The difference between a useless scan and a perfectly calibrated medical image comes down to a single physical process: the precise control of invisible radiation. Every time an X-ray beam is emitted, its total output and the resulting exposure is under the direct, manual control of the radiologic technologist. That control operates through three prime variables: milliampere second, or mAs, kilovoltage peak, known as kVp, and the source-to-image receptor distance. These are the operator's levers. Relying on machine presets or blind guesswork to set these levers is a liability. Clinical rigor requires understanding the actual physics happening inside the tube and across the room. By mastering the physical laws governing these three factors, you stop guessing. You gain the ability to mathematically guarantee optimal image exposure for any patient anatomy. We begin inside the X-ray tube with mAs. This lever is made of two distinct parts: milliampere, representing electrical current, and time, measured in seconds. The mA dictates exactly how many electrons boil off the tungsten filament. The S dictates exactly how long that cloud of electrons is allowed to flow across the tube. Combined, mAs acts as the absolute controller of X-ray quantity. It dictates the total volume of photons created when those electrons finally strike the metal target. The clinical rule here is direct proportionality. If you double the mAs, you produce twice as many photons, and you exactly double the exposure to the image receptor. These three radiographs show this relationship. The kVp is locked, only mAs changes. In image A, mAs is 1.1. In image B, at 4.7, density increases as more photons hit the receptor. Pushing mAs to 10 in image C severely overexposes the result. mAs is the linear workhorse of radiography. It scales the sheer volume of radiation up or down in a perfectly predictable straight line. The second prime factor, kilovoltage peak, or kVp, introduces a new layer of complexity to the system. If mAs represents the number of electrons in the tube, kVp represents the force driving them across the gap. kVp controls the quality, or penetrability, of the beam. Higher energy electrons create higher energy photons, which are required to punch through thicker, denser anatomical tissue. Increasing the kVp simultaneously boosts penetrability and the efficiency of photon production at the target. This dual effect means that adjusting kVp alters both the quality and the quantity of the beam, resulting in a highly nonlinear impact on the final image. To manage this exponential behavior in a clinical setting, technologists rely on a strict heuristic: the 15% rule. The rule states that a 15% increase in kVp will double the exposure to the image receptor. It achieves the exact same exposure chains as doubling the mAs, but uses a fraction of the raw electrical adjustment. Figure 12-2 tests the rule. Image A uses 60 kVp and 10 mAs. In image B, kVp increases 15%, so mAs is halved to 5 to maintain density. Image C ignores the math. kVp increases, but mAs stays 10, rendering it dangerously dark. kVp is a volatile lever. Because it dictates tissue penetrability, you must use it to adjust contrast, but you have to actively deploy the 15% rule to prevent it from exponentially overpowering the image receptor. Our final prime factor happens outside the tube housing entirely, the source-to-image receptor distance, or SID. Once X-ray photons exit the window of the tube housing, they do not travel in a perfectly straight, tightly packed laser beam. They diverge. Because the beam continuously spreads outward, the actual intensity of radiation falling on any specific square inch of the detector drops drastically as the distance increases. This drop-off is not an estimate. It is governed by a rigid law of physics known as the inverse square law. Figure 12-3 proves intensity is inversely proportional to the square of distance. Doubling distance from D1 to D2 forces the same photons to cover an area 4 times as large. Consequently, radiation intensity in any square becomes exactly 1/4 the original. Distance is a highly destructive variable. If you move a tube further from a patient without compensating, you will completely starve the image receptor of the radiation it needs to form an image. This creates a major clinical dilemma. If a trauma patient on a stretcher requires the X-ray tube to be moved much further away than standard room protocol, how do you prevent the resulting image from being underexposed? The solution is the exposure maintenance formula, sometimes called the direct square law. It allows you to rescue the exposure. To maintain a constant density on the image receptor when distance changes, you must adjust your mAs so that it is directly proportional to the square of the change in distance. Figure 12-4 shows this compensation. We compare image A at 40 inches to image C at 72 inches. To maintain density, mAs was increased from 2.5 to 8. This sharp increase is the direct mathematical result of the square law restoring beam intensity. Distance dictates the baseline intensity of your beam. When physical reality forces that distance to change, mAs is the compensatory tool you use to save the image. In a clinical setting, mAs, kVp, and distance never operate in a vacuum. They are a single, interconnected physical system. Pull one lever, and you must push another. Increasing the distance means you must drive mAs upward to fill the void. Increasing your kVp by 15% means you must immediately slash mAs in half to avoid flooding the detector. mAs scales radiation quantity in a perfectly straight line. kVp dictates penetratability and bends exposure exponentially through the 15% rule. Distance degrades baseline intensity through the rigid geometry of the inverse square law. Memorizing the formulas is a baseline requirement, but the ultimate goal is visualizing the physics. Seeing the electrons boiling off the filament, feeling the driving force of the voltage, mapping the divergence of the beam as it crosses the room. When you stop guessing at console settings and start manipulating these three physical properties directly, you achieve the core competency of radiologic science, transforming raw physics into vital diagnostic truth.